Welcome to our next segment, which covers security and AI tools to use while building your smart contracts. So I'll go over a little bit of consensus smart contract best practices. I've also left another guide here for more in-depth detail for developers, and then also show a little bit about auditing with AI auditors. So let's jump into it. Here is the Ethereum smart contract best practices document. Just to start off with this document provides a baseline knowledge of security considerations for intermediate Solidity programmers. It is maintained by Consensus Diligence with some contribution from the broader Ethereum community. So where to start? In this video, I'll explain a little bit more about the general philosophy, which describes the smart contract security mindset. And then there are also additional sections that I would not cover in this video, which you guys are more than free to go ahead and study yourselves. This is like the development recommendations that contains examples of good code patterns, known attacks that describes the different classes of vulnerabilities to avoid, and then some of the security tools that they list to improve your code quality and detecting vulnerabilities. So let's move on to the general philosophy. So as you all know, Ethereum and complex blockchain programs are new and are highly experimental. Therefore, you should expect constant changes in the security landscape as new bugs and security risks are discovered and new best practices are developed. Following the security practices in this document is therefore only the beginning of the security work you will need to do as a smart contract developer. Smart contract programming requires a different engineering mindset that you may be used to. The cost of failure can be high and the change can be difficult, making it in some ways more similar to hardware programming or financial services programming than web or mobile development. It is therefore not enough to defend against known vulnerabilities. Instead, you need to learn a new philosophy of development. So let's jump into their philosophy. Prepare for failure. Any non-trivial contract will have errors in it. Your code must therefore be able to respond to bugs and vulnerabilities gracefully, such as a circuit breaker pattern. This is a pattern where you can pause the contract where things are going wrong. There's also other different patterns, such as rate limiting and maximum usage, where you manage the amount of money that is at risk. And you should also have an effective upgrade path for bug fixes and improvement. Stay up to date. Keep track of new security developments. Check your contracts for new bugs as soon as it's discovered. Upgrade to the latest version of any tool or library as soon as possible. Adopt new security techniques that appear useful. And always also keep it simple. Complexity increases the likelihood of errors. Ensure the contract logic is simple. Modularize the code to keep contracts and functions small. Use already written tools or code where possible. Example, don't roll your own random number generator. That's where something like an Oracle, such as Chainlink, would be beneficial to use. Prefer clarity to performance whenever possible. Only use the blockchain for parts of your system that require decentralization. Rolling out your smart contract. It's always better to catch bugs before a full production release. Test contracts thoroughly and add tests whenever new attack vectors are discovered. You could also provide bug bounties starting from alpha testnet releases. Roll out in phases with increased usage and testing in each phase. Blockchain properties. While much of your programming experience will be relevant to the Ethereum programming, there are still pitfalls to be aware of. Be extremely careful about external contract calls, which may execute malicious code and change control flow. Understand that your public functions are public and may be called maliciously in any order. The private data in the smart contracts are also viewable by anyone. Keep gas costs and block gas limit in mind while designing these contracts. Be aware that timestamps are imprecise on the blockchain. Miners can influence the time of execution of a transaction within a margin of several seconds. Randomness is non-trivial on the blockchain. Most approaches to random number generation are gameable on the blockchain. Now, moving on to the final point of their philosophy, which is simplicity versus complexity. There are multiple fundamental trade-offs to consider when assessing the structure and security of a smart contract system. The general recommendation for any smart contract system is to identify the proper balance for these fundamental trade-offs. An ideal smart contract system from a software engineering bias is modular, reuses code instead of duplicating it, and supports upgradable components. An ideal smart contract system from a secure architecture bias may share this mindset, especially in the case of more complex smart contract systems. However, there are more important exceptions where security and software engineering best practices may not be aligned. In each case, the proper balance is obtained by identifying the optimal mix of properties along contract system dimensions such as the rigid versus upgradable, monolithic versus modular, duplication versus reuse ability of the contract system. Rigid versus upgradable. While multiple resources, including this one, emphasizes malleability characteristics such as scalable, upgradable, and modifiable patterns, there is a fundamental trade-off between malleability and security. Malleability patterns, by definition, add complexity and potential attack surfaces. Simplicity is particularly effective over complexity in cases where the smart contract system performs a very limited set of functionality for a predefined limited period of time. For example, a governance-free, finite time frame token sale contract system. Monolithic versus modular. A monolithic self-contained contract keeps all knowledge locally identifiable and readable. While there are few smart contract systems held in high regard that exists as monoliths, there is an argument to be made for extreme locality of data and flow, for example, in the case of optimizing code review efficiency. As with the other trade-offs considered here, security best practices trend away from security engineering best practices in simple, short-lived contracts and trend towards software engineering practices in the case of more complex, perpetual contract systems. Duplication versus reuse. A smart contract system from a software engineering perspective wishes to maximize reuse where reasonable. There are many ways to reuse contract code and Solidity. Using previously deployed contracts, which you own, is generally the safest manner to achieve code reuse. Duplication is frequently relied upon in cases where self-owned previously deployed contracts are not available. Efforts such as the OpenZeppelin Solidity library, as we discussed earlier, seek to provide patterns such that secure code can be reused without duplication. Any contract security analysis must include any reused code that has not previously established a level of trust commensurate with the funds at the risk in the target smart contract system.